Welcome to this short but hopefully informative presentation on McCready, which is all about the optimum speed to fly. I hope you learned some new facts about McCready. Paul McCready first described the optimum speed to fly selector in 1954. The aim of this presentation is to give you an insight into the usefulness of McCready, plus an understanding of its importance in cross-country flying. You will require a McCready ring attached to your variometer, and it will look something like this. An electronic variometer with built-in flight director is more the modern state of play. Task data is shown on the instrument with the speed to fly flight director shown here on the right. You will also require an ASI so you can follow McCready's speed to fly as accurately as possible. Amongst other things, McCready relies on your judgment skills and interpretation of the sky ahead. The better your judgment on reading the sky, the more accurate will be your McCready setting, resulting in a faster cross-country speed. You will also need to understand the term tangent. The speed polar uses tangents to define best speed to fly for any given rate of climb or rate of descent, or any given headwind or tailwind component. Here, a tangent to the polar curve is showing the best glide speed for one crew member and no water ballast, i.e. lightest wing loading. To understand McCready, we must first understand polar curves. Here are the topics we will explore throughout this presentation. Let's remind ourselves of the relationship between angle of attack and lift. Lift increases with increasing angle of attack until approaching the stall, where further increase in angle of attack causes lift to rapidly reduce. The relationship between airspeed and lift is not linear. Lift increases proportionally to the square of the airspeed. The relationship between airspeed and drag is not linear either. Total drag increases with increasing airspeed, hence the curve of demise in performance. I've chosen the geodiscus as an example with a dynamic cockpit load and water ballast capability. I've also chosen the geo because I have access to the polar curve data. Just like the geodiscus, your glider will also have a flight manual. And from that flight manual, here is the actual polar diagram for the geodiscus. Here are a few fixed and variable values affecting the polar of a glider. Can you think of any other influences which may affect the polar? That's right, bugs, ice, dirt, amongst other things. Here we have a polar for minimum wing loading. Minimum sink speed is approximately 43 knots, but more importantly, best glide speed is approximately 50 knots. As shown by a tangent with its origin at 0 on the vertical speed scale. Adding a second crew member has increased the wing loading. We need to fly faster for lift to equal weight. The wing hasn't changed shape, therefore the polar must move down and to the right. Net result is our best glide is now 54 knots. Adding full water ballast has increased our wing loading to its maximum. Our best glide speed is now 61 knots. Overlaid on top of each other, we can see how the polar curve moves down and to the right with increasing weight. Here is an easy concept to explain best speed to fly. We start at A, we glide to B, and we climb to C. With McCready set to 1 knot, for no other reason than to keep the calculations simple, We can now use 60 knots as our cruising speed for the next examples. Let's say two pilots are flying identical gliders through the exact same air mass. Pilot number 1 stops in every thermal. Pilot number 2 stops only in the strongest thermal. Both pilots take 15 minutes to cover the 15 nautical miles flying at 60 knots. However, pilot 1 spends 12 minutes 30 seconds climbing, and pilot number 2 spends 7 minutes 30 seconds climbing. McCready says thermal strength is all important. For those who answered the rhetorical question, B to C is the most important, well done. Let's analyse what actually went on during this time. Items shown in green are those which they got correct. Items shown in red are the mistakes they made. Let's look at 4 identical gliders flying at different speeds between thermals, and let's crunch the numbers. To identify each individual glider, they have been given appropriate names. They all start at A at the same time. Who is going to be the first to arrive at B and start climbing in the thermal? Here is an animation depicting the glide from A to B. The timing has been scaled 60 to 1, i.e. for every second on the screen it would be 1 minute in real time whilst flying. As you've just seen, McCready is not the first glider to reach the thermal. However, it arrives much higher and before minimum sink or best glide. Comparing the time taken to climb from B to C, the lowest glider takes an extra 2 minutes and 16 seconds to climb the difference. Overall, A to C, there is 2 minutes 42 seconds difference between the slowest and fastest glider. Here we've increased wing loading to maximum, and we've set McCready to 2.1 knots. Note the tangent no longer intersects the origin. It now intersects the vertical axis at the McCready value 2.1 knots. Here is the same polar expanded to show the origin at plus 2.1 knots on the vertical axis. Note that best glide is now 38.3 to 1, but it is being achieved at 84 knots. Here we have increased McCready to 4.1 knots, and best glide has increased to 96 knots and is now achieving 32.7 to 1. McCready has now been increased to plus 6 knots. Best glide speed is now 101 knots, achieving 30.5 to 1. Note that beyond this speed, performance reduces rapidly. We've determined that thermal strength and speed to fly are all important. So for those of you who chose A to C as the answer to the rhetorical question, well done. McCready is primarily all about guessing the next thermal strength, then gliding at the optimum speed to reach the climb at the height which will allow you to arrive at cloud base quickest. You could use your crystal ball combined with your judgment skills, or you could make use of your electronics package and the averager. How then do we choose an accurate value for the next climb? Which value do you enter into McCready for your next expected climb? Here we can see the instantaneous rate of climb and the average rate of climb, and of course it's the average we're interested in using. When listening to stories of cross-country flights, you'll always hear the instantaneous values being used to impress. Let's now look at headwind. Here we can see the tangent has moved along the x-axis and the origin is at plus 27 knots. Check out the best LD. tailwind, the tangent has moved left. The origin is now -27 on the x-axis, giving a reduction in speed to fly for best glide. Now check out your best LD. Here is a basic variometer setup without any compensation. We know what the glider is doing with respect to climb and descent. Let's now introduce a calibrated tube into this system that will control the airflow in and out of the variometer, depending upon airspeed. The airflow will create a low pressure by the two holes in the tube. The intensity of this pressure is dependent upon airspeed. The low pressure will suck air out of the tube until balance is reached. We now have a system that accounts for what the air mass is doing and not just the glider's vertical excursions. To put it another way, having removed stick lift, we can now dolphin fly with confidence. Applying McCready ring settings involves rotating the ring until the reference marker points at the expected rate of climb of the next thermal. The variometer needle will then point at the speed to fly for any given moment in time. The modern variometer will switch between the cruise and climb functions. This may be done manually, but more normally is automatically selected by flap selection or airspeed measurement. The flight director will also give a speed to fly indication. The principle of dolphin flying is to fly McCready speeds between thermals and to slow down in the lift, stopping to climb at the lower end of your operating height band, or when lift encountered is greater than your chosen McCready setting. In less favourable conditions, when you find yourself descending below your operating height band, slow down and be conservative. If you find yourself extremely low, go into survival mode, take a weak climb, and stay in that climb until you can reach something better. Once you're back within your height band, revert back to flying McCready settings. Rejection of lift is quite often more important than accepting lift. Either way, we need to decide when to reject lift, when to dolphin climb, and when to stop and climb in the stronger thermals. For final glides, the concept of A to B to C is very similar, but this time we climb from A to B and we glide from B to C. The burning question is, how high do we climb and how fast do we glide home? Best glide is the speed at which you will cover the greatest distance, so therefore must be the earliest time you could level your wings on a final glide. However, it won't get you home quickest. Let's say we've reached the height that will allow us to get home using best glide, but we're climbing in a 4-knot thermal. How high do we climb before we set off, and how fast do we glide home? McCready states that for a 4-knot thermal, we need to climb an extra 1,305 feet and glide at 81 knots. In doing so, we beat best glide by 3 minutes and 44 seconds. Here is an animation of climb and final glide. The time scale is 60:1, and overall there is 10 minutes and 43 seconds between the slowest and fastest gliders from A to B to C. McCready says thermal strength of the last climb dictates the height to start and the speed to fly on your final glide. In reality, we're going to be final gliding from far greater distances than 20 nautical miles. Here are the figures for a 40 nautical mile final glide. As you can see, dolphin flying will be necessary, unless of course you can cloud climb. Left of the diagonal white line is below glide, right of the diagonal white line is above glide. The principle of final glide dolphin flying is to fly McCready between thermals, slow down in the lift, stopping to climb when lift greater than McCready is encountered. If you're falling below glide, slow down until glide has been regained. Then continue flying at McCready. Hopefully, we've covered each aim to the point where you've understood the basic principles of McCready flying. In conclusion, to fly McCready accurately, you need a good knowledge and understanding of the weather. You have to follow the energy. If the thermal strength is stronger than your chosen McCready setting, stop and climb, and consider increasing your McCready setting. And remember to set McCready to the last thermal strength for your final glide. The mathematics proves that the fastest achievable cross-country speed is when you fly to McCready. The perfect McCready flight is probably impossible, but nothing can beat McCready, so it still remains the ultimate goal. I'll leave you with this closing statement. Thank you for watching. I do hope you've learned something useful about McCready, and I hope it improves your cross-country flying and your overall cross-country speed. Happy landings. Oh, and one last thing. When you have one of these in your hand, you're entitled to talk instantaneous rates of climb.